Hello, my name is May Makani, and today we'll be talking about regulating the send rate. So first off, how do we regulate the sending rates to obtain a desirable bandwidth allocation? The sending rates may be limited by two different factors. So the first factor is flow control, in the case that there is insufficient buffering at the receiver. The second case would be congestion. In that case, there is insufficient capacity in the network. So to talk about briefly about the difference between these two, we can see the problem illustrated hydraulically, right? So in this figure, we can see a thick pipe leading up to a small capacity receiver right here. This is a flow control limited situation, which is one of the ones we just saw before. As long as the sender does not send more water than the bucket can contain, no water will be lost. In figure 2, the limiting factor is not the bucket capacity, but the internal carrying capacity of the network. So if too much water comes in too fast, it will back up and some will be lost. In this case, it would overflow this funnel. So when a congestion signal is given, the sender should decrease their rates. The way in which the rates are increased or decreased is given by a control law. These laws have a major effect on performance. So when the signal is rate to use, it would be the XCP protocol. And here in this figure 623, we can see some of the signals for different protocols when it comes to congestion control. AIMD, additive increase, multiplicative decrease. It is the appropriate control law to arrive at the efficient and fair operating point. In 1989, a graphical argument was constructed for the simple case of two connections competing for the bandwidth of a single link. So the bandwidth allocated to user 1 is on the x-axis, would be this one, and user 2 on the y-axis. So in this first case, when the allocation is fair, both users will receive the same amount of bandwidth. So it would be right about here. And that is shown by the dotted fairness line that I just showed. When the allocation sum up to 100, the capacity of the link and the allocation would be efficient. This is shown by the dotted efficiency line. A congestion signal is given by the network to both users when the sum of their allocations crosses the line. The intersection of these lines is the desired operating point, when both users have the same bandwidth and all the network bandwidth is used. So when the efficiency is to 100%, it would be the same as the x-axis. The same would apply if it decreases to here. In this next example, 625 would be for the AIMD control law, the bandwidth allocated to user 1 on the x-axis and the user to the y-axis the same way. When the allocation is fair, both users will receive the same amount of bandwidth. This is shown by the dotted fairness line as shown before. When the allocation sums to 100, the capacity of the link, the allocation is efficient, just the same way. This is shown by the dotted efficiency line. A congestion signal is given by the network to both users when the sum of their allocations crosses the line. The intersection of these lines is the desired operating point. When both users have the same bandwidth, all the network bandwidth is used. As we can see, the difference between this one and the previous example we saw would be the additive increase and decrease. So lastly, a question. What are the two factors that limit the sending rate? The answer would be right in the first slide. Flow control and congestions are the two factors that limit the sending rate. Thank you so much for watching.